Hello, good morning, good afternoon, good evening, everybody, wherever you might be. Well, our speaker is now at the Pacific Coast, so it's an early morning for him. It is my great pleasure to welcome Benjamin Anderson-Sackany, who simply is going to speak about C-star simplicity and boundary actions of discrete quantum groups. The Zoom is yours, the floor is yours. Take it away.
Thank you. And thanks for the introduction and give me a chance to speak in this seminar. So yeah, talking about C-star simplicity and boundary actions. So first, let's begin with the main motivation, which is coming from groups and their reduced C-star algebras. But first, just a bit of a notation. So I'll be talking about the reduced C-star algebra of a discrete group and eventually that of a discrete quantum group. But anyway, this is the notation. And associated to it, we have this Haar state, which is often in the operator algebras literature referred to as the canonical trace. And we denote it by this, H, but it's also often denoted by delta E. And it's basically just the state that's concentrated on the identity element. And we'll be making use of the adjoint action for groups commonly known as the conjugation action, and it's given by conjugation by your group on the reduced C-star algebra like this. So A time, I'm using this convolution symbol, convolved with G is equal to G inverse AG, like that, conjugation. So we're going to have a notion of a boundary action, and I'm not going to define that right now, but I'll talk a bit more about it later. And in particular, we have the Furstenberg boundary action, which is a very special boundary action, important for all of this theory. So it seems that the starting point for C-star simplicity is with this result of Powers in 75 is he proved that the reduced C-star algebra of the free group on n generators is simple with a unique trace. Or he might have done it just for F2, but it's true for all free groups on finitely many generators. So this gives rise to the definition of C-star simplicity. We say a group is C-star simple if its reduced C-star algebra is simple as a C-star algebra, so it has no closed two-sided ideals. And so let me just make a very brief comment about what Powers did to prove this. And what he did to prove this is he showed that we have the following strong approximation averaging property. So what he showed is that for all elements of the reduced C-star algebra, if you evaluate the Haar state, get the scalar, multiply it by 1, it can be realized by the closed convex hull of all of the conjugations of that element by the group. So what he did is he showed that the free group and n generators had this very special property, and this property ended up being extremely important for C-star simplicity. So for example, for a while, this was the main method for proving C-star simplicity, but it turned out that this was actually a very deep observation. As we'll see in the next slide, it turned out that C-star simplicity implied this property as well. So anyway, so for a while, that was the main method for showing C-star simplicity of groups. And then a bit later, it started becoming apparent that group dynamics was a useful tool for looking at this sort of problem. And eventually, Kalantar and Kennedy found this beautiful characterization of C-star simplicity. They showed that G is C-star simple if and only if G acts topologically freely on its Furstenberg boundary. And I quickly wrote down the definition of this. It means that the interior of all of the points fixed by G is empty for all elements in your group. And okay, this is a nice theoretical result. The only drawback is that the Furstenberg boundary is often very difficult to understand. It's a large space, non-metrizable when it's non-trivial, etc. But if you can find a topologically free boundary action, then you can learn that G is C star simple. And this is a result that's good for proving examples. So as an example, it is actually fairly easy to see that the free group of n generators acts topologically freely on its Gromov boundary. So the compact set that you get by taking the infinite words on Fn. You can just directly show that it acts topologically freely on this compact space. And it shouldn't be too hard to prove that it's a boundary either. So this is the point is this is a very nice result for proving C star simplicity. And okay, and then moving a bit forward, like I said before, we get that Power's averaging property is equivalent to C star simplicity. This was the result of Kennedy and independently by Holgrup. But there ended up being another property, kind of involving boundary action, and namely that involved these boundary maps. And those also turned out to characterize C star simplicity and also have found use for characterizing sort of topologically free actions sort of outside of the context of boundary actions. But anyway, in this case, of boundary actions, G acting on the Furstenberg boundary, we have the following. Things are equivalent. So as I said, G of C star simple, G has Power's averaging property, and there exists a unique G covariant UCP map going from the reduced C star algebra to the continuous functions, the G C star algebra of continuous functions on the Furstenberg boundary. And namely, it's the one where you send a...
Sorry, I'm a bit confused. May I stop you here?
Okay.
I don't understand what is the logical meaning of what you write in parentheses. Do you assume that it has to be a map of this particular kind, like with values in scalars, or is it just an example of a G equivalent UCP map?
Right. Yeah. So I guess I didn't make that clear. So what I mean is that there exists a unique J covariant UCP map, and it's the one in the brackets.
And that's the one in the bracket. Okay.
Yeah. Yeah. And that is always an example, but when it's unique, it is equal to that one.
So this map is okay. So it always exists, but it has to be unique. So the uniqueness is the catch. Okay. Thank you.
Yeah. 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 So there exists a unique J covariant UCP map like this, and this map where you send A to the Haar state like this, it always exists. So when it's unique, it's going to be equal to this one.
Yeah.
And well, it turns out you can extend these J covariant UCP maps to the cross product by the Furstenberg boundary. And what you get are J covariant conditional expectations from the cross product to the Furstenberg boundary. And so this is equivalent to the uniqueness of these G covariant conditional expectations. And then it's a result of Pitts and Zarikian that you can get rid of G covariance. So just simply there exists a unique conditional expectation, not necessarily a covariant, from the cross product to the Furstenberg boundary, or the G C star algebra of continuous functions on the Furstenberg boundary. Okay, so this is sort of the main theorem I wanted to highlight in this motivation. So this will come up again. And the question is, well, what about in the quantum setting? Can we recover any of these previous results for discrete quantum groups? And kind of a very important question along these lines is, what is a topologically free boundary action of a discrete quantum group? So what is the right notion of a topologically free boundary action that we can actually use to get these results? So you can note that there is some notion of a topologically free action for locally compact quantum groups on a C-star algebra, but it's not readily usable for this theory of C-star simplicity. We're looking for something that's really useful for this. Okay. So this is the main motivation. Now let's actually get into the main topic of this talk. But first, I'm going to say some stuff about discrete quantum groups so that we understand what we're working with. So let me just recall that the reduced C-star algebra of a group is this should be the closed span, by the way. It's the closed span of all the unitaries of the group elements coming from the left regular representation. And I'm going to do something that seems a bit odd at first. Thank you. Is I'm going to consider these group unitaries to be unitaries on B of L2 of G, but amplified trivially like this. So we add in a tensor by the scalars. So this, why I'm doing this will be apparent in a second, but I just want to have this in mind. So we're going to start with a discrete quantum group, and I'm not going to do some axiomatic definition of one. I'm just going to give you what objects come with a discrete quantum group. And by the way, this is going to be the operator algebraic definition. There's going to be construction coming from the operator algebraic compact quantum groups due to Voronovich. So I'll explain in a second why I'm going with discrete quantum groups versus compact quantum groups. All right. So with all that, we start with the discrete quantum groups. Then there exists the following: a Hilbert space, U of G hat, which are some set of so-called irreducibles. We won't worry about the part about it being irreducibles, but this has meaning.
Sorry, Ben, there are two questions. So Tomek was first, I believe.
Oh, okay.
My apology. My question
is, what?
Yes, my apology. My question is elementary, but maybe you pointed out and I didn't hear your explanation. Is there a reason for consideration of the tensor product for complex with complex number? Because BL2G is itself a complex space.
Yeah, this is meant to sort of prime us for something I'm going to mention that's not so trivial in a second. So there is a reason. It is trivial in the case of groups, but it won't be trivial for quantum groups, is the whole point.
Yes, yes.
Yeah.
Tomek?
Yes, yes. Yes.
It was also my question.
Okay.
Okay. Yeah. So actually, so we're okay?
Yeah, go on.
Okay.
Yes,
so
yes,
actually,
it's good. Thank you.
Yeah. So we're exactly at the point actually where this comment about the tensoring with the scalars is not so trivial for quantum groups. So we have U of G hat. This is a collection of unitaries. And instead of being a collection of unitaries on B of L2, they're collections of unitaries amplified by a matrix algebra. So for this, we have this sort of set of unitary operators, and each of them has this dimension NU, and this dimension in the quantum case is at least larger than 1. Some of them can be equal to 1, but if it's a true quantum group, some of them will be larger than 1. So
okay, Adam.
Sorry, may I also have a question?
Yeah, go ahead.
Sure.
About this collection of unitaries. So you mean all possible unitaries or only some sub-collection?
So it's just going to be some collection of unitaries, some collection of these dimensions.
So this notation is very confusing, since it suggests that this is some object canonically associated with this G.
I mean, Adam, it's not a definition, it's an explanation.
Yeah, so if you start with a discrete quantum group, then you can get this collection of unitaries.
Exactly.
Okay.
Definition, if you're starting axiomatically, you would have started with a C-star algebra and a coproduct and whatever, and then you prove that this collection of irreducibles exists. So I'm just assuming we already have a quantum group.
Okay.
Tomek.
So probably it would be easier to understand if it would be irreducibles of G hat equals a collection of unitaries.
Right, yeah. Maybe I should have put
G,
some
yes.
collection.
Yeah,
Oh.
exactly. Yes.
Yeah, it's some collection. Yeah. Okay. Hopefully this is clear now. If we put
Yes.
some collection.
Yes.
Okay. And well, we do basically the kind of non-commutative version of the reduced C-star. Again, this should be a closed span. Wasn't very careful with that. So the reduced C-star algebra of discrete quantum group is the span of all the matrix coefficients of this collection of unitaries, acting on these amplified versions of B of L2 of G. And, this turns out to be a C-star algebra. And this is going back to my comment about compact quantum groups and the construction due to Voronowitch. This is really just the Voronowitch C-star algebra on the compact quantum group G hat. But I want to sort of focus my perspective on the discrete quantum group G. So this is the reduced C-star algebra of G. But if you're used to compact quantum groups, this is C of G hat, the reduced C-star algebra in the sort of the theory of Voronowitch's compact quantum groups. Anyway, so this is the reduced C-star algebra, and you replace unitaries with coefficients of unitaries is the whole point. So we have this, and there's a coproduct, delta hat. We won't really be working with the coproduct too much. And then there is a Haar state generalizing the canonical trace from groups, and it's defined by being a state and the fact that it's invariant with respect to the coproduct. These should be delta hats here. And it's uniquely determined by satisfying this invariant condition. So this Haar state
here, right?
Yeah, that's right. Thank you.
So it's a joint talk after all.
Yeah, I should have put you on the first slide. So basically, this is how we construct the reduced C-star algebra for discrete quantum groups. And we have this associated Haar state, and the Haar state will be very important. So we need to remember these two things basically. So this is the reduced C-star algebra. It's basically the compact side. And then on the discrete side, we have a von Neumann algebra. And this is a quantum group in terms of the von Neumann algebraic notion due to Customer and Voss. So if you take the L infinity direct sum of all the matrix algebras corresponding to each of these irreducible things, then we get a von Neumann algebra, and this turns out to be L infinity of G, the associated von Neumann algebra of the discrete quantum group. And then on this side, we also get a coproduct. And I will be making use of this coproduct. So these are the operator algebras associated to a discrete quantum group on the discrete quantum group side, and then it's reduced C-star algebra, which is sort of on the dual side, the compact quantum group side. I'll be working mainly with the reduced C-star algebra, but we do have to understand L infinity of G. So these are the basic objects. Moving on. So remember before, the Haar state for groups is tracial. So things commute inside the argument is called the canonical trace. But this sort of property doesn't necessarily hold for discrete quantum groups in general. And when it does, we call this the Katz property. So we'll say that G is Katz type if H is tracial. So really, I think it's more natural to consider some other definition to be the Katz type property, and this is equivalent, but this is the definition we're going with. And all right, so with the co-product, we can define convolution just like we define convolution for groups, which is where you have a natural way of multiplying measures together using the group action. So L1 of G will define it to be the pre-dual of L infinity of G, the pre-dual, and then the probabilities measures of G, so quantum probability measures will be exactly the normal states on L infinity of G. And
so just a stupid question. The pre-dual of matrices is again matrices, right?
yeah. So I guess trace class operators, but it's still vector space matrices.
Yeah.
I just wanted to be very exact.
I like it. It's just sanity check. I just want to make sure.
Yeah. And so we define convolution using the co-product like this. You take their tensor and pre-compose with the co-product. This gives you a product. And in the case of groups, this recovers the notion of convolution you might be used to. Probability measures are closed with respect to star. That's obvious because tensor of states is a state, and then you're pre-composing with a star homomorphism. And we're going to, in particular, look at finitely supported probability measures. And so if you look at this L1 decomposition of L1 of G into these, matrices, basically you're just taking finite sums of these matrices, and we call these finitely supported probability measures.
Sorry, I have a question regarding this convolution. I think that something is missing. Shouldn't it be a function of one variable?
Yeah, so the co-product.
As you defined it.
So co-product takes in one variable.
Into two variables.
Okay, and then you apply this tensor product and
then these are number valued, these are functions. So that's why they just multiply naturally. Typically, you would also put multiplication at the end, but you don't have to because they are scalar valued functions.
Okay, that's
Yeah.
why. That's why. Okay,
Yeah.
okay. I was missing this multiplication. Okay.
I'm sorry, Ben. Again, I'm doing a job. I'm sorry.
That's okay. Yeah, technically there should be a multiplication in there, but
here it can be skipped.
it's somewhere where I'm consistently lazy. Okay. All right. So with all of that out of the way, I want to actually look at some specific examples of some discrete quantum groups. And the examples I'm going to look at will play the role of free group and N generators. And this will be the main example that we'll look at the end of this talk. As a test case for the results that we're looking at. So first of all, let's consider the free group and N generators and some finitely generated discrete group G. And so then, well, the reduced C-star algebra of G is this C-star algebra, the closed star algebra generated by its elements, Gi. So it's not the span, it's the algebra generated by this subset of G. And Fn satisfies this universal property by mapping generators to generators. There exists a surjection from, and I'm going to write it like this, from the group ring of Fn to the group ring of G. And it maps generators to generators, but we can express that by writing it out like this. We have that phi sort of respects the co-products, intertwines them. Okay, so
here, this C-star algebra is actually, it gives you, because it's the convolution C-star algebra, it gives you a compact quantum group, right?
That's right, yeah.
And if you don't mind me throwing in a very quick but irrelevant comment, perhaps, is that for these compact quantum groups, because we know their K-theory, I mean, K1 is just given by these generators, we could actually prove by K-theory that these compact quantum groups are not contractible. in general, it is not known. I mean, it's a classical result in group theory that the only contractible compact house of topological group is the trivial group. And we expect the same to be true for compact quantum groups. But we have classes of examples, like, I know, quantum deformations, for instance, and another class of examples given by free groups when we actually prove that they are not contractible.
Okay. Well, thanks for that comment. It's interesting. All right. So the quantum version of looking at a finitely generated discrete group is looking at what I'll call finitely generated discrete quantum groups. And if you're used to the compact quantum group side, these are your compact matrix quantum groups. This is just the duals of those. So anyway, a finitely generated discrete quantum group is one where you fix one of these unitaries. So reduced C-star algebra tensored with a matrix algebra Mn, and then the reduced C-star algebra is the C-star algebra generated by the coefficients of this unitary. So it's generated by a single unitary operator, kind of like these irreducibles from before, but it's not necessarily an irreducible. Okay, so in sort of this language, we can view finitely generated groups as the following. So if G is generated by G1 to Gn, then you can just take the diagonal matrix. So in this picture, your groups are the finitely just generated discrete quantum groups generated by diagonal unitary matrices. And so out of this framework, we can define free unitary discrete quantum groups. And they're sort of the freest versions of finitely just generated discrete quantum groups that you can define through this framework. So the notation I'll be using is FUF, and well, so they're the duals of free unitary compact quantum groups, the compact matrix quantum groups commonly from the literature, but I'm considering the dual side. So this is the notation for that. And there are certain quantum groups where you take some invertible matrix and then you just take by some universal construction this unitary matrix such that, well, F U bar F inverse is unitary, and U bar is just the matrix where you take the adjoint of all of the coefficients. And this is basically the only restriction that you put on the unitary. And you end up getting a discrete quantum group called the free unitary discrete quantum group.
But this is just a direct modification of what Shuzu Wong discovered in his PhD thesis, right?
Yeah. This is...
Okay.
Yeah. All right. So then... Okay, so we can talk about the Katz type discrete quantum groups. And when are these cats? Well, they turn out to be Katz type if and only if F is a scalar multiple of a unitary. And for all intents and purposes, you can just think of the Katz type case as being the case where F is an identity matrix. And you get in the literature, these would be FUN, FU capital N, or in the case where F is the identity matrix. And so, yeah, we get lots of these examples. And just like for free groups and N generators, these satisfy this universal property. So the full family of free unitary discrete quantum groups gives us a universal family of quantum groups for finitely just generated discrete quantum groups. So more precisely, whenever you have a finitely generated discrete quantum group, then there is one of these free unitary discrete quantum groups and a surjection on their quantum group rings. So I didn't formally define the quantum group rings, but it's just the non-closed version of the reduced C-star algebra. So actually, I guess technically before I was defining the quantum group rings, but anyway, such that we have that the surjection respects the coproducts. So mimicking what we have for the free group and N generators and finitely generated discrete groups. And then also, what was shown by Bonica is that all of these discrete quantum groups are C-star simple with a unique sigma KMS state. And I didn't define what a sigma KMS state is. This will come up a bit later, but the point is, this is something that generalizes the unique trace property. And these free unitary discrete quantum groups have these properties, just like the free group and N generators.
So, sorry, not going into detail about this definition of sigma KMS state, but could you only explain what is sigma? This is some automorphism, or?
Yeah, it's a modular automorphism associated to the Haar state. And instead of being tracial, it's a twisted variant of the tracial condition using this automorphism. So I'm going to explicitly write down what I mean later.
Okay, thank you.
Yeah. All right. So the whole point is we have these examples, free unitary discrete quantum groups, and they're a lot like free group on N generators, which makes them a good test case for this stuff regarding C-star simplicity. So we'll come back to these examples later. And also to give you sort of a hint of how you can naturally build examples of discrete quantum groups, or I guess more like the compact quantum groups associated to them. They're C-star algebras. Okay. All right. So now let's talk about actions. So how do we formulate the notion of an action for a discrete quantum group? Well, let's go back to what we can do with actions of groups on compact topological spaces. So let's say we have G acting on X, a compact topological space. And from this, we can obtain a unital star homomorphism going from C of X to the multiplier algebra of C0 of G tensor C of X. And it's given by the following formula, alpha F evaluated at Sx is just multiplication inside of F, or the group action S acting on X inside the argument of F. And well, okay, so we can define this map, and the key property that it satisfies from our point of view is that we can define this generalized convolution F convolved with mu, where where mu is an L1 function, by taking this sort of slice map on alpha F. And this turns out to be an L1 of G module map, viewing L1 of G as an algebra. And this makes C of X a G C-star algebra. So we're looking at G acting on X, and we're seeing how G also acts on C of X. And this is the perspective that we use to define quantum group actions. So given a unital C-star algebra, we say that A is a G C-star algebra and write that G acts on A if there exists a star homomorphism on the C-star algebra level, much like with C of X, such that we have this generalized convolution that is an L1 of G module map.
And
like
please
above.
correct me if I'm wrong, but I don't believe you need commutativity of the C-star algebra. You could put any A here, say unital, if you want to be compact.
Yeah, you could. Yeah. And then you would have G acting by star automorphisms on the non-commutative C-star algebra. Yeah.
Exactly.
And then, all right, so below, I technically didn't define C0 of G, but this is just a C0 direct sum of all these matrix algebras. So before I define L infinity of G to be the L infinity direct sum, well, C0 of G is just the C0 direct sum.
So wait, so is it here just algebraic?
What's that?
Is it just algebraic direct sum here?
No, it's C0 direct sum. So you take the C0 norm and then...
So vanishing at infinity. Okay.
Yeah, vanishing at infinity.
Jacek? Go ahead.
Hi, I wanted to ask about two things. So one is if this definition that you write here below, is it equivalent to assuming that alpha satisfies the usual coaction property?
What's the question?
You define action of a discrete quantum group on a unitary sister algebra, and my question is if this definition is equivalent to another one when you have this kind of star homomorphism alpha, but you assume that it satisfies this coaction condition, meaning that you compose alpha with identity tensor alpha equals delta tensor identity composed with
Right,
alpha, if
yeah.
these two definitions are equivalent.
Associativity, right? Yeah.
Yeah. So the L1 of G being a modular map, that should be equivalent to this co-associative kind of condition, the coaction condition. But you do have to include some extra properties to get the Podgell's condition, which I'm ignoring here just for brevity.
Okay, so out of this, you wouldn't get necessarily Podgell's condition.
No, you would need some extra properties.
I see. And if I may, another condition, do you assume alpha is injective or not really?
Very good question. Yes.
Yeah, good question. Yeah, it should be injective. Yeah, that's a good question.
Okay, thank you.
Yeah, those are good questions. Thanks for asking them. All right. So I'm relying a little bit. You need a little bit more extra properties for this to be an actual quantum group action. But these are sort of the main important points for us, is that we have the star homomorphism, and then we get this action of L1 of G on A. Okay, let's move on. So we could talk about G-C-star algebras and equivariant maps. So we'll say a map from a G-C-star algebra A to a G-C-star algebra B is G equivariant if this L1 module map, if it's an L1 module map with respect to these sort of generalized convolutions. So phi of A times F is phi of A times F. And so I'm abusing this word convolution a bit too much, but we can define convolution on the states, on the state level. So given G acting on A, we can let F times var phi, be convolution where we just replace the coproduct with this coaction alpha.
Yep.
So for F, L1 of G, inside of L1 of G and var phi in the dual of A. And then this convolution sort of respects the states as well. So F times var phi is inside the state space of A, where F is a probability measure and var phi is a state on A. All right, so now let's look at the most important example here is going to be the adjoint action, which I've already mentioned for groups, and also the coproduct is an example. So given that G acts, so we have that G acts on the reduced C-star algebra via this adjoint action, which we can write out like this. It's given by this sort of conjugation by this unitary. And we could write this unitary basically as the direct sum of all the unitaries, of all the elements of U of G hat. So in particular, if G is a discrete group, then this adjoint coaction is given by taking the direct sum over all the conjugations of G on A. So we really do recover the conjugation action with this adjoint action. And as before, G acts on, as I mentioned, G acts on L infinity of G by the coproduct. So this adjoint action is what's important for us.
And now, sorry, the same stupid question again. And this direct sum is in which category?
L infinity.
L infinite.
Yeah, should be a von Neumann algebra. So all of this lies inside of B of L2 of G, tensor L2 of G. This whole formula. All right. So I'm just still, okay, so we're basically through the preliminaries now. Let's remind ourselves of what the motivation of all this was again, so just so we can have this back in our brains. So remember, we have this characterization of C-star simplicity in terms of topologically free boundary actions. And in particular, we can observe C-star simplicity by finding a topologically free boundary action. And we can do this explicitly with the free group and N generators. And then we have these characterizations of C-star simplicity in terms of powers averaging property and these G equivariant UCP maps going from the reduced C-star algebra to the G C-star algebra of continuous functions on the Furstenberg boundary. So we're going to look at these sort of things for discrete quantum groups now. So first of all, let's look at the development of boundaries for discrete quantum groups. And I'll actually start off by giving you a definition of a boundary action, at least one at the G C-star algebra level. So it turns out that G is a boundary, X is a boundary action of G if and only if every G equivariant UCP map from C of X to L infinity of G is completely isometric. So we have this rigidity on the sort of embeddings of C of X and L infinity of G, and consequently onto any G C-star algebra. And then the Furstenberg boundary is the universal boundary action. So it surjects onto every boundary of G, every G boundary. And so this is equivalent to saying, well, all the C of X's of boundaries embed G equivariantly inside of the continuous functions of the Furstenberg boundary. And equivalent formulation of the Furstenberg boundary is that it's the G injective envelope of the trivial action, or of the scalars with the trivial action. And so if you're not familiar with this sort of thing, this basically means that it's G injective in the category of G C-star algebra with G equivariant UCP maps, and it's the smallest G injective thing that contains the scalars. But everything is unital here, so that part is for free. Okay. Well, actually, not just G C-star algebras, G operator systems. But anyway, it's a G injective thing, and it's somehow minimal. Well, using the fact that it's a G injective envelope allows us to define it for discrete quantum groups. Right. So, okay, so this note I just made, this is due to Hamana and Kalantar and Kennedy. And then later, Kalantar, Kasprzak, Skalski, and Vernieu, they generalized this theory to discrete quantum groups. So we define the Furstenberg boundary to be the G injective envelope of the scalars. And then boundary actions are just the G C-star algebras such that all of their embeddings inside of L infinity of G is completely isometric. And we end up getting that this is equivalent to them having a G equivariant embedding inside of the Furstenberg boundary. Okay, so we have this theory of boundaries that works just like the discrete group case for discrete quantum groups.
And sorry, and who is KK in the first note?
Kalantar Kennedy.
Kalantar Kennedy. So not
Yeah.
Kalantar Kasprzak, okay.
No, yeah. So this is going to be a pattern. I'll introduce the citation at some point and then reduce to the letters. But I'll try to say it verbally what they are each time.
Mm-hmm.
Okay. So, right. So we've had success so far with defining boundary actions. The question is, all right, how can we successfully use them now for the theory of C-star simplicity? Let me show you somewhere where they have been fully successfully used, and they've been successfully used for this unique trace property, which is a property deeply related to C-star simplicity. Again, goes all the way back to Powers with his observation that Fn has the unique trace property as well as C-star simplicity. So first, for a definition, we will say a Katz type discrete quantum group has the unique trace property if whenever you have a tracial state, it's equal to the Haar state, which is tracial by definition. And for non-Katz type discrete quantum groups, you could come up with the unique trace property. It's just that there isn't a canonical choice because then the Haar state isn't tracial. So it's much less clear as a property, I suppose. But for Katz type discrete quantum groups, we just mean that the Haar state is the only tracial state on the reduced C-star algebra. So, okay, so I'm going to mention both the quantum and the classical versions at the same time. And so this is how we've seen the use of boundaries so far. Let G be a Katz type discrete quantum group. Then we can characterize the unique trace property in terms of G acting faithfully on its Furstenberg boundary. I'm not going to define faithfulness, but it's weaker than acting topologically freely for, at least for classical discrete groups. Okay, so this is the one point where I break my rule. I didn't write out Brulard, Kalantar, Kennedy, and Ozawa earlier, but that's BKKO 17. And is in their work that we have the classical result for discrete groups, and then Kalantar AL, Kalantar, Kastchuk, Skelsky, Vernieu, they did one direction of this theorem, and then myself and Khosravi, we did the other direction of this theorem. Okay, and then as a consequence of this, you can then prove that if G is C-star simple, then it has the unique trace property. So when we first started looking at C-star simplicity and unique trace property, it was conjectured that they were actually equivalent. We didn't have any examples for quite some time where a group had the unique trace property but wasn't C-star simple. But there ended up being a counterexample, and eventually we were able to prove that C-star simplicity implies unique trace property. So their relationship was unclear for quite some time up until BKKO 17. And the counterexample that I'm not going to put in the slide. Okay, so I put a note of this here. Unique trace property does not imply C-star simplicity. And well, as a result, going beyond the Katz type case, just for arbitrary discrete quantum groups, which was resolved very recently, just a couple of months ago. If G is C-star simple, then G acts faithfully on its Furstenberg boundary. So just to explain, so myself and Khosravi, we proved this result for discrete quantum groups with the approximation property, and then also in the Katz type case, or for exact discrete quantum groups, and also the Katz type case. And the row is able to extend the results to arbitrary discrete quantum groups not that long ago. So the question.
And your assumption, what was your assumption about
that the reduced C-star algebra is exact? So exact. Yeah. Which covered basically all known examples at the time, but now we know this in the arbitrary case. So the whole point is, all right, boundaries have been successfully used to study a unique trace property and also resolve this question of C-star simplicity implying the unique trace property. So there is hope that, well, boundary actions is useful for studying these sorts of questions for discrete quantum groups. So now let's go back to focusing on C-star simplicity. So I'm going to introduce cross products a bit more formally now. So given G acting on A, where we have this coaction alpha, we can construct the reduced cross product exactly like this. And I'm going to point out that there exists a faithful conditional expectation going from the cross product to the copy of A inside of it. So I'm identifying A with alpha A. And it satisfies the following formula. If you restrict to the reduced C-star algebra, it's just the Haar state. This turns out to be a G-C-star algebra, so G acts on it by this sort of adjoint action using the same W that we saw for the adjoint action. And A and the reduced C-star algebra have G equivariant copies inside of inside the cross product. So
Wait, I'm confused. Wait a second.
okay.
So here A is a C-star algebra, and when you write beta of A, isn't A an element?
Oh, yeah. I didn't realize that when I was writing. Yeah, so maybe this A, beta A should be beta T or something. That should be a different letter.
Okay.
Yeah.
Yeah, because this A belongs to the whole cross product, right?
Yeah. Yeah, so this A, I should be using a different, but it's an element of the cross product. Yes.
Mm-hmm.
So maybe it should be X or so. I just didn't want to put little a. Anyway, yeah.
Mm-hmm.
So this is the story of cross products. And then it turns out this conditional expectation is G equivariant if and only if G is Kapp's type. So this will be very important. And continuing on, when you look at the cross product by the Furstenberg boundary, specifically, we end up getting a bijection between the following sets of maps: G equivariant UCP maps, so these boundary maps going from the reduced C-star algebra to the Furstenberg boundary, and then G equivariant conditional expectations going from the cross product by the Furstenberg boundary to itself. And I mean specifically, it's onto the Furstenberg boundary. Right, and this follows from the special categorical properties of the Furstenberg boundary. All of such maps extend by G-injectivity, and then by the special boundary properties of the Furstenberg boundary, they end up being conditional expectations. So we can pass for free basically between these G equivariant UCP maps and these G equivariant conditional expectations. And so sort of as the last relevant result that I know of regarding C-star simplicity, it turns out that reduced C-star algebra is simple if and only if this cross product is simple. Oh, I meant to put the corresponding result for the reference for groups, because this is a known result for groups as well. This would be, I think this should be in BKKO, so Brillard, Kalantar, Kennedy, Ozawa, I believe. All right. So, as far as I'm aware, this is basically what we can say about C-star simplicity so far. Now let's actually move on to the stuff that Roland and I had done. And
so you begin your talk right now.
Yeah, this is all of the background stuff. And let's actually move on to the new stuff. So first, I want to remind us about Power's averaging property, because I'm about to write down a quantum group version of it. So we can sort of do this rephrasing of it. So for all self-adjoint elements, so just by linearity, you can go to self-adjoint elements. And before, the definition was that the Haar state of A can be obtained by these closed convex Hall of all the conjugations of A by your group elements. We can write this in terms of the infimum over all of the finitely supported probability measures via this generalized convolution. So Haar state of A is obtained by all the convolutions of all of the finitely supported probability measures against A. or approximated by it. And so, like mentioned before, if G has power averaging property, then it's C star simple with the unique trace property. And this property turns out to be equivalent to C star simplicity. So let's move on to quantum groups. So first, let's define this special set of probability measures on G. And if we're going to define sort of this stabilized set of probability measures, stabilized by convolution against the Haar state. And I'm going to be using the word stabilized to refer to sort of the property of being stabilized by the Haar state by convolution. Anyway, this is the set of all probability measures where when you convolve against the Haar state using the adjoint action, you just get the Haar state. So all the things fixed that have the Haar state as a fixed point. Well, it's known that G is Katz type. It's been known for some time through the work of Izumi that G is Katz type if and only if this is every finally supported probability measure. So basically, H is a fixed point for the adjoint action, or it's in a G invariant state. And so here's what we can do. We can find Power's averaging property, just like in the classical group case. It's the infimum. This is verbatim. Where the infimum over all of the convolutions of F against A. But we also want to define a stabilized version of Power's averaging properties, PAPH, where instead of going over the infimum over all probability measures, you go over only specifically the stabilized ones. So clearly, the stabilized version implies the full version, and if G is Katz type, then these two properties are equivalent because, well, the two sets are equal.
Yeah, now, let me ask you some stupid questions again. Is it possible that this space of probability measures with this extra H condition is empty or just trivial or just one element, something? What is sort of the minimal, the opposite of Katz type?
So it has at least one element because there's the
H.
co-unit.
Co-unit, sorry.
Yeah, always multiplies against H. But we can find whole families of states that belong to this set. You can just write them down explicitly. So there's a lot of these states floating around. Yeah,
And can you convolute H with itself, or?
So H is a state on the reduced C-star algebra, and F is an element of these probability measures. So
okay, so this is just a different. Okay.
It doesn't.
Yeah. Thanks.
Yeah. Okay. So we have these we're going to have these two versions of Power's averaging property floating around. Okay. So, all right. So finally, I'm going to define a sigma KMS state. So H is a sigma KMS state. And by that, I mean, we have this twisted version of traciality. And here, sigma T is the modular automorphism group of H. You extend it analytically to complex numbers. And so H has this twisted version of the tracial property. And well, G is Katz type if and only if this modular automorphism group is trivial. That's very clearly equivalent to traciality of H. Okay, so that's what I mean by the sigma KMS state is having this twisted traciality property, or deformed by this modular automorphism group.
There's
a question, I think, Jacek.
Yeah, sorry, can I ask a question about the definition?
Sure.
Can you go back with the slide?
Sure.
So I'm wondering if I'm missing something, but what is the why do you assume that A is self-adjoint in this definition? Would it be equivalent without this assumption?
So for the powers averaging property, it is equivalent. We do, or for the stabilized version, it is equivalent. But we do run into some problems with the non-stabilized version with the self-adjointness. So we want to assume self-adjointness at the start. So when you're trying to do linear arguments with powers averaging property, we run into trouble. So there is like, there are some problems with this in the non-stabilized case, basically. So we want to do it on the self-adjoints, and then trying to extend to not to just arbitrary elements, you run into some issues. Yeah.
Okay, thank you.
Yeah, that was a good question. I didn't address that at all before. Okay, so just like with discrete groups, if discrete quantum group has the powers averaging property, then it is C star simple, and then it turns out that H is the only possible tracial state on the reduced C star algebra. So this isn't too hard to prove. So as part of the proof, you have to use some result of mine from one of my own papers to get that H is the only possible tracial state. We have this. And then if she has the stabilized version of powers averaging property, then it's C star simple, and we have a unique sigma KMS state. So it's with the stabilized version of powers averaging property that we get this generalization of C star simplicity with, instead of unique tracial state, we have this unique KMS state. So at least this part all works with powers averaging property. And well, it turns out that if you actually go through Bonica's paper, where he proves that the free unitary discrete quantum groups are C star simple with a unique sigma KMS state, you can actually see that he actually proved that they have this stabilized version of powers averaging property. Mm-hmm. This is really what he had done. He just never defined this version of powers averaging property. And let me make a note of something along these lines. He actually did define some analog of powers averaging property, and this was at the level of looking at the co-representation theory and combinatorics on them. And he noted that these examples did not have this property despite being C star simple. So we at least found some version of powers averaging property that they did have. I just wanted to make a quick note of that. Okay, so this is powers averaging property. Now let's go and look at these boundary maps. So G is C star simple. So something that's not too hard to prove is that G is C star simple if and only if every G covariant UCP map, all these boundary maps are faithful. The property of interest is uniqueness, that there exists a unique G covariant UCP map of this form, so that there's only one. Well, what we noticed is that there's another property that's potentially the one of interest, and I'll try to justify that. And namely, it's this property, we will say a UCP map from the reduced C star algebra to the first Berg boundary, not necessarily G covariant. You don't need that for this definition. We'll say that it factors H if it factors H basically. So if you take the set where you apply all the states of the first Berg boundary to this map, then you eventually get H. Or another way to put it is you take the adjoint of this map and its restriction to the state space of the first Berg boundary, then H is an element of the image of that map. So as a quick note, if H factors this map, one of these maps, then it's faithful. It follows from faithfulness of H. And well, this is what we're able to prove for powers averaging property. So first of all, we have that G has powers averaging property if and only if all of the G equivariant UCP maps from the reduced C-star algebra to the first Merge boundary factors H. So rather than it being equivalent to uniqueness of a G equivariant UCP map, we have this factors H property instead for all the maps. And it's in the case of a CATS type discrete quantum group that we get that it has the powers averaging property if and only if there exists a unique such map. So in the CATS case, we get a bona fide generalization of the corresponding theorem for discrete groups. But for arbitrary discrete quantum groups, it seems that we have to replace this uniqueness property with this factors H property instead. So this is the story of powers averaging property so far. But what about the stabilized version? Well, there is a bijection between G equivariant UCP maps from the reduced C-star algebra to the first Merge boundary and G boundaries, so compact topological spaces that are G boundaries inside the state space of the reduced C-star algebra. And I'll come back to this in a second. This was one of the essential observations of Kennedy, or one of his main theorems, is this. In his paper where he proved powers averaging properties equivalent to C-star simplicity. So let me mention one of the defining properties of a G boundary that I haven't really mentioned is namely strong proximality. So this is one of the things you can take as part of the definition of a G boundary is that, well, if you take any probability measure on X, then you can recover the rest of the probability measures by taking the closed orbit of all the convolutions of probability measures of G by this fixed measure. There's a strong proximality. So having pointed that out, so if we look at this theorem and we're trying to think of how to generalize this to quantum groups, you realize that as it is stated, it just wouldn't make any sense because, well, if you have the state space of the reduced C-star algebra of a discrete quantum groups, boundaries are not necessarily commutative, so it doesn't make sense to try to find G boundaries in the state space. You don't have these topological spaces to consider. So what we'll do instead is we'll take this boundary envelope approach, which are basically subsets of the state space of the reduced C-star algebra that are defined to have this strong proximality condition. And so you can make this definition without the stabilization, so just G boundary envelope and prob CG invariant subset K. And we will also do it with the stabilized version, so GH boundary envelope and the stabilized probability measure invariant subset K, such that we have the strong proximality condition. So we're going to consider these two variants of this sort of definition. And so if you just look at the singleton with the Haar state, this is the trivial GH boundary envelope. That's the trivial one. So the idea is going to be we're going to replace G boundaries with these GH boundary envelopes, or G boundary envelopes.
But they are still topological spaces, right?
So the boundary envelopes are convex subsets of, so I'm going to say exactly in the next slide the relation to G boundaries. So G boundary envelopes are exactly the closed convex envelopes of G boundaries. So if you start with the G boundary envelope and you take the closure of the extreme points, then you get a G boundary. So you can pass between these two concepts like this. And so one of the observations of Kennedy, one of his results is that G has the powers averaging property if and only if the only G boundary in the state space is trivial, if and only if the only G boundary envelope is trivial. Right. And so this was actually how he proved that the powers averaging property is equivalent to uniqueness of a G covariant UCP map and also its relation to C-star simplicity. Well,
wait, just to make sure that I understand your logic. So you are saying that this PAP is equivalent to the equivalence.
say it again. So PAP.
You say that G has PAP.
Yeah.
If and only if the equivalence holds between, you know.
Oh no. So what I'm saying is these three things
all of them are equivalent. Okay.
Yeah.
Okay.
Right.
Okay.
That's probably a good clarification. Thanks. Okay. So the connection to G-covariant UCP maps is the following. There exists a bijection between G-boundary envelopes inside the state space and G-covariant UCP maps from the reduced C-star algebra to the first Berg boundary. And the relationship is as follows. Given a G-boundary envelope, it is given exactly by taking the adjoint of one of these G-covariant UCP maps, taking its restriction to the state space of the first Berg boundary, and it's the image of that. And so just to really spell things out, we have that X is trivial if and only if it has H as an element. That's from the strong proximality condition. And then this is equivalent to psi just being the Haar state. Right, so that's how all of these concepts relate together. Okay, so now here are the complications for quantum groups. So there exists a bijection between G boundary envelopes and G covariant UCP maps like this, except that if you don't look at the stabilized version of these, then you don't get that H belonging to X implies X is trivial. In the stabilized version, if X is a GH boundary envelope, then we do get that X being trivial is equivalent to H belonging to X, but we lose this bijection between these GH boundary envelopes and G covariant UCP maps going from the reduced C-star algebra to the first Berg boundary. So there's a connection, but not a bijection. And so that's a complication. Nevertheless, we have this characterization of the stabilized version of powers averaging property, namely it holds if and only if each of these GH boundary envelopes is trivial. Okay, so that's the story of powers averaging property. So now let's move on to free actions, topological free actions. And this is the million-dollar question. What is a good quantum analog of a topologically free boundary action?
No. Sorry. Who is the sponsor? Who gives $1 million?
I think it might be a vacuous $1 million or something. Yeah. It would be nice if someone could give us $1 million for this. All right, so let's start off with a naive candidate. I'm not going to go through this definition. The whole point is that there is some definition of a free action. And in the classical case, it's equivalent whoops. So A here should be C of X. So G acts topologically freely on X if and only if G acts on C of X freely in the above sense.
Yeah, but this is what we discussed a week ago with Matthew Kennedy. I mean, we have a well-established concept of a free action of a quantum group on a C-star algebra. So here what you're doing, it's not this freeness, it's topological freeness. So why do we call it free if it's topologically free?
Right, yeah, so this seems to be just established nomenclature already. So there's some paper of what was it, Tomatsu and some other guy, they defined a notion of a free action on von Neumann algebras, and it's basically just this definition, and they call it freely acting. And then there's a paper of Zurichian that this generalizes the definition of for groups acting on non-commutative C-star algebras, and he also calls it a free action. And so we're calling it a free action just because of that, even though it should be topological freeness. Yeah, I don't have a good answer for that.
Yeah, but this is very bad because, for instance, first, if you want, it goes much earlier. But say the official definition was published in a Journal of Functional Analysis 24 years ago. So if you have a concept which has been established for decades, you cannot just hijack the name and use the same name for something which means something different. When was this paper about von Neumann algebras published? When was it?
Close to 2000. I forget the exact year, so it was like 20 years ago, I think. And this paper, Zurichian, was only like 5 years ago. I mean, we don't really like this. We don't really like calling it free actions either. But we elected to just kind of go with what was already in the literature.
Yeah, but other things are also in the literature. Tomek, what's your question?
Yeah.
My question is about not about freeness, but your freeness is topological free boundary action.
Okay.
So it is supposedly is much more than being even free in a naive sense. So how an example of a free action in your sense could be an analog of topological free boundary action?
Right. So you could have this definition for a G boundary, and then that would be a definition of a topologically free boundary action. So that does make sense. So you can do that using this definition.
So I don't understand this naive candidate.
Oh yeah. So the whole point is
for what? It's
so
a full package topological free boundary action, or it's a some kind of freeness condition.
Right. So what I'm going to get at is that for trying to define a topologically free boundary action for quantum groups, it's tempting to use this definition, and it's not going to turn out to be the right one. But there's still something interesting about it. That's what the story of this is going to be.
Mm-hmm. Okay.
Maybe I should just continue, and then you'll see what I mean.
Mm-hmm.
So let's move on. So basically, we have this theorem, and this generalizes a result of Zurichian. We can characterize this notion of freeness as the following. So we have number 2, which I don't really want to focus on. What I want to focus on is that it's equivalent to the existence of a unique conditional expectation of the cross product, A of G with A onto the GC-star algebra A. So remember, this non-equivariant version of uniqueness of a conditional expectation showed up in the list of equivalences of C-star simplicity. So note that there always exists a G-equivariant conditional expectation of the cross product with the Furstberg boundary to the Furstberg boundary. And as a consequence, if this action, the Furstberg boundary action, is free in this sense, then in particular, because this canonical expectation always exists, it must be G equivariant, because also a G equivariant one always exists, and there's a unique one, hence G is Katz type. So in the non-Katz type case, we can never get this version of a topologically free Furstenberg boundary action. So for this, and another problem that we ran into is we weren't sure if the following is true. If G acts freely on a boundary, then does it act freely on the Furstenberg boundary? We weren't able to answer this question. And so for these reasons, we believe that maybe this isn't the right notion to consider, right? It has no hope of working beyond the Katz case, and we have examples of non-Katz type discrete quantum groups that are C-star simple. We would like to be able to study those examples as well. So I'll leave this at this, but there is kind of an aside I want to make, is the techniques that we used for this theorem turn out to have an interesting application. So it's not really a total loss. So let's go back to faithful actions. And let me make a note first about some things. So it turns out that a state on the reduced C-star algebra is tracial if and only if it's a fixed point by this adjoint action, by convolving by probability measures on G. So Kalantari al, Kaspersky, and Vernieu, they proved this in the Katz case, and I generalize this to arbitrary discrete quantum groups. That's what the reference there is for. And as a consequence of this, we get that if tau is tracial, then it extends to some G equivariant conditional expectation on the cross product. So every tracial state is the restriction of some G equivariant conditional expectation. So we can rephrase, at least in the Katz case, the following result, that unique trace property is equivalent to G acting faithfully on its Furstenberg boundary. So G acts faithfully on its Furstenberg boundary if and only if there exists a unique G equivariant conditional expectation on the cross product, satisfying the property that it restricts to a state on the reduced C-star algebra. So we can rephrase this result like this. I just want to point that out. And then we get this generalized version for arbitrary G C-star algebras. So we get that the following are equivalent, that G acts faithfully on the G C-star algebra. You know, we have 2, which is kind of a weakened version of the corresponding result for free actions. But then it's also equivalent to the existence of a unique conditional expectation on the cross product, satisfying the property that it restricts to a state on the reduced C-star algebra. So this is kind of like a generalization of the unique trace property. You just express it in terms of these conditional expectations. So this is something that kind of just fell out of this for us. So I'll move on from this now. So now what I want to introduce is something that we think might be the correct notion of a topologically free boundary action. And I'm going to start with the inspiration for this. So we can define, instead of trying to work with generalizing topologically freeness, we can look at this notion of strong faithfulness. So we see an action is strongly faithful if for every finite subset excluding the identity of G, there exists some point that observes that such that it doesn't fix any of the elements of this subset. So G of X is not equal to X for all G and F. So let's list out some facts. So this property is implied by topological freeness. It's not equivalent. However, in the presence of minimality, it is equivalent. So a boundary action is strongly faithful if and only if it's topologically free. More generally, a strongly faithful minimal action is equivalently topologically free. All right, so it is using this observation that we're going to try to define a topologically free boundary action for quantum groups. So let's try to generalize. It's not too hard to generalize strong faithfulness. So here's how we can do it. So we're going to define strong C-star faithfulness. And I'm not going to go into the definition in detail, but what I will highlight is how the different parts of the definitions correspond to each other. So the blue part is the part that is saying that we have a finite subset. I didn't write finite, but it's a finite subset excluding the identity. That's what this stuff about the finite right projection is saying. And then in olive, we're choosing an element X. So we choose a norm one positive element, and then we have to do some amplification. And there's some, to get the examples we wanted to work, we had to do this version of it, but this is what we have. We have this sort of stabilized version. And then the part where g of x is not equal to x for all g and f, we can write it out like this, and we do it quantitatively. So we have these etas, these positive numbers, and we have that the norm of this operator is getting small by choices of A.
What does this lower index 1 means?
Oh, it means norm one.
Oh, okay.
Yeah, norm one positive element.
And norm 1, okay.
Yeah.
Could you, Ben, could you help me? I'm looking still at this definition of a strongly faithful action. And how would you weaken it to become just faithful? So what would you drop here?
Well, so
I
F
understand
would
that
be,
everything strongly faithful is faithful, so but not the other way around. So where is the strongness? Which condition gives you the strongness adjective?
so instead of, so faithful would be you just take points, so just singletons. Strongly faithful
Singletons, and
means
here any finite. Okay.
finite subsets. Yeah.
Okay. Yeah, thank you.
And I thought I didn't write finite subsets. I did write finite. Anyway, okay. So this is our definition of a strong C-star faithful action for quantum groups. I don't necessarily need us to fully comprehend the definition, but this is the definition, and it is inspired by a strongly faithful action for groups. So as hoped, G acts strongly faithfully on a compact topological set space if and only if it acts strongly C-star faithfully on the G C-star algebra C of X. And so to really reiterate myself, the moral is that we will think of a topologically free boundary action as being a strongly C-star faithful boundary action. That's what we're going to use here.
And in your definition of strong C-star faithfulness, this epsilon is a counit, right? The counit.
That's right. Yeah.
Okay.
Yeah. That's the part that's excluding the identity. Okay. So moving on. So here's our theorem, or yeah, one of our theorems. So it turns out if G acts strongly C-star faithfully on a G C-star algebra, then every conditional expectation on the cross product is such that its restriction to the reduced C-star algebra factors H. So this factoring H property is coming back, and don't need G equivariance for this. So it might be that this property of having a unique conditional expectation might need to be replaced with this factoring H condition. So as an observation, it's obvious that if G acts strongly C star faithfully on a boundary, then it acts strongly C star faithfully on the first Berg boundary. That's just because there's an inclusion, and you're choosing elements in the smaller one means you've chosen elements in the bigger one. And well, as a corollary of this, then we get that if G acts strongly C star faithfully on a boundary, then G has the powers averaging property, hence is C star simple. And I'll actually spell out the proof just to remind ourselves of the various results going into this. So by the observation, G acting C star strongly C star faithfully on a boundary implies the same on the Furstenberg boundary. That's step one. Step two, by the above theorem, every conditional expectation on the cross product with the Furstenberg boundary to the Furstenberg boundary is such that its restriction to the reduced C-star algebra factors H. And then we had a theorem earlier that this property implies G has the powers averaging property, because then this would be true of all the G equivariant conditional expectations. Okay, so all of this stuff comes together right here. Okay, and so we have this theoretical result. So if you can find a strongly C-star faithful boundary action, then you can get powers averaging property. And that's the next thing that we did. So let's go back to these examples of free unitary discrete quantum groups. So first of all, there's this question of, we have these notions of quantum Gromov boundaries, and it's a question, it's a sort of a non-trivial question to ask of whether or not they're G boundaries in the sense of this talk. So
could you remind me what is a classical, not quantum, Gromov boundary?
Right, so if you look at the free group acting on its Gromov boundary will be this sort of all the set of infinite points. You get a compact topological space, and that turns out to be a boundary for Fn in this sense. So the set of infinite points. And there exists a quantum analog of this for the free unitary discrete quantum group. And it's defined in essentially the same way, where instead of infinite points, you look at infinite points of, you get the coefficients of infinite combinations of the irreducibles. And it's much more complicated to actually write it down, but the idea is the same, as kind of going off to infinity by multiplications of your group elements or your irreducible elements. All right, so anyway, the Gromov boundary for Fn is a boundary action. And if you look at the free unitary discrete quantum group, its quantum Gromov boundary, well, it was already known that it's a boundary in some other sense that I won't say exactly what this is. This is something due to Havestad, Hateshi, and Neshveyev. So they had proved this, and this is weaker than it being a G boundary in our sense. So up to this point, it wasn't known yet whether or not it was a G boundary in our sense, but also G boundaries were only just recently discovered. And in the paper of Kalantar, Kapstruk, Skelsky, Vernieu, okay, I didn't define the free orthogonal discrete quantum group. It's basically an analog of the free unitary discrete quantum group, but you have some self-adjoint condition in the generators, and it has a quantum Gromov boundary. And it was a highly involved result in their work that this action is actually a boundary action in this sense. And they also proved that it's faithful. So they got the unique trace property for these examples. I'm just going to quickly mention that these examples are known to be C-star simple with unique sigma KMS state, given some restrictions on F. So it's not known that all of them are C-star simple. That remains open. anyway, going back to the free unitary discrete quantum group, so we were able to show that it acts strongly C star faithfully on this quantum Gromov boundary. And the other thing that we were able to show, which is actually, so point one is actually not that hard. We just use some observations of Bonica, but point two is non-trivial. This part is hard. Is that at least for when n is greater or equal to 3, so f needs to be large enough, then we get that these are boundary actions. So this is a new result, and this is really the hard part of this theorem. So in particular, we cover a non-stable analog of Bonica's result, right? So this implies powers averaging property, but not the stabilized version. So that's the sort of one caveat of this. But we've demonstrated that. So we have this notion of a topologically free boundary action, and it appears to work in this test case. So this is kind of the punchline to this. And yeah, I'm done here.
Thank you very much. Okay. Any further questions from Jacek, Tomek, Adam, whoever? Oh, Jacek, go ahead.
Thanks for the talk. Maybe first I wanted to ask, so you mentioned that free unitary quantum groups have powers averaging property. Do you know if free orthogonal quantum groups have this property?
So we know that the Katz type ones do, but we're not sure about the non-Katz type ones. So if you look at the Voss and Vernieu paper, they do prove that it has something that looks like powers averaging property, but it somehow involves both the action of G and the opposite of G opposite. So in the case where G is Katz type, you can see how you just end up getting just the action of G on the reduced C-star algebra. Yeah, so and the whole point is that they build a map involving both G and G op, and somehow use that to prove some analog of powers averaging property. And it's not clear that you can recover just powers averaging property out of that argument. Yeah, but in the Katz case, you can do it.
Okay, thanks. And second question, if I may. You work with this first boundary. So I understand that there are theorems stating its existence, but is it possible to describe it somehow concretely in some cases, like, I don't know, Q deformations or unitary quantum groups?
Very good question.
Yeah, good question. No, it's like, it seems it's just too big to like really have a concrete description of it. It's like that's the main drawback of the first merge boundary, is that you just really can't work with it on like an example level. It works really nicely at a theoretical level because it has these nice properties, G injectivity, and then the fact that it's a boundary and stuff like that. But yeah, you just really can't write it down in examples. That's why it's desirable to find examples of G boundaries, like Gromov boundaries, and like these quantum Gromov boundaries, proving that they're boundaries. That's why doing this sort of thing is desirable, because trying to just write down the first merge boundary is too hard.
So in particular, it will often be non-separable?
Yeah, I believe so.
Right.
And what if your group is finite, or quantum group is finite?
Then it's trivial. So if
It's
G,
trivial.
I should have mentioned this. If G, it is trivial if and only if G is amenable.
Okay.
Yeah. So it's only interesting in some sense outside of the amenable case.
So this means that for Q deformations, you do have description. It's true.
Yeah. True.
Yeah, exactly. Okay. Tomek?
Okay, so I have two questions. The first one continues this line of questioning of Jacek. My question is, what can be said about the invariance of the topological free action on C of this Furstenberg boundary in the classical case?
The invariance.
Yeah, fixed point subalgebra. Yeah, I also wanted to ask this question. Yeah.
So what's the question? Can you rephrase the question anyway?
So you have an action of your group on continuous functions on this Furstenberg boundary. So what are invariants of this action?
The invariants?
Could you say anything about?
Yeah.
What is the fixed point algebra?
Yeah.
Fixed point subalgebra. In this topological free context, at least.
Yeah, so it should be trivial in the topologically free context. Yeah.
Okay.
And
wait, so the only fixed points are complex numbers? That's what you mean?
Yeah. Yeah, and this should be true when it's faithful as well. I'm just trying to think if it's ever non-trivial.
So topological free means something like ergodic action.
Yeah.
Okay. My second question is about this relation between C-star simplicity and this convolution, this cross product. So did you try to go outside the CATS or KMS case, allowing some cross products with cocycles?
No, we didn't try to look at cross products with cross cycles. No, we just stuck with what I presented pretty much. But maybe there could be something interesting there.
Yeah, so usually there are some cocycles coming from the context of your problem, but in this case, I cannot imagine this kind of cocycle related to your problem.
Yeah, I don't know either.
Okay, thank you.
Anybody else? Well, if not, let me ask you a question. So you can use the Pontryagin duality. I mean, every discrete quantum group is just Pontryagin dual to a compact quantum group. So how much and to what extent you could say conveniently rephrase whatever things we are talking about in the context of discrete quantum groups into their dual compact quantum groups. Perhaps, so for instance, what is the simplicity of a discrete quantum group in terms of its compact dual?
So in terms of the compact dual,
maybe it's completely pointless. Maybe it's inconvenient. Maybe it doesn't do anything. But somehow, at least theoretically, you can ask such a question.
Yeah. So I mean, just by definition, it would just mean that C of G hat, or your Aronovich C-star algebra, is simple, or at least the reduced version, where you take, say, the GNS representation of the higher state and take the reducing map. That is simple. That would just be the reformulation. But are you looking for like some other characterization that would be?
Sorry, simple meaning what?
Yes. Okay. So that's right now I see my confusion. Yeah, because when you say C star simple, let me write it down. You say that your group is C star simple. The convolution, the reduced convolution C star algebra is as simple as a C star algebra. So that's of course basically the same as Voronovich's C of G hat. So
you're asking if C of G hat.
so my question was wrong. I mean, it's just tautological. This is that simplicity of the C-star algebra. Okay, sorry. Yeah. Because somehow in my mind was that you say C-star simple if the function algebra, you know, C naught of G is simple, but that's not what you mean. Okay.
Yeah.
That's not what you mean.
This really is like a statement about the compact quantum group.
Yeah.
It's just.
So in fact, your talk is about simplicity of the sister algebras of abelian compact quantum, no, of compact quantum groups simply.
Yeah, pretty much. It's just because of how things need to be phrased in terms of like boundary actions and stuff like that. It's easier to talk about things from the perspective of the discrete quantum group because you're talking about discrete quantum group actions. Yeah. And also, I guess as kind of like a strategic point is for someone who's used to discrete groups and C-star simplicity. For the classical case, we wanted to write out things in terms of the reduced C-star algebra discrete quantum group to make the analogy apparent there as well. So there is that too.
Yeah, so you have a classical case would be abelian compact quantum groups. Yeah, they are dual to discrete groups.
Yeah.
Yeah, but for finite case, I suppose it's about Maschke theorem, about simplicity of the group algebra.
Good point. Good point. Okay, I think it's time to wind it up. So let us thank our speaker again. Let me choose. Oh, yes. Okay, so thank you so much.
Thank you.
Stop the recording.